Ever wondered who laid the foundations for modern geometry? Meet Euclid, the ancient Greek mathematician. Born around 300 BC, Euclid's influence towers over the field of mathematics like a colossus, even though we know surprisingly little about his life. What we do know is largely derived from references in the works of other scholars, painting an enigmatic portrait of a man whose mind was leagues ahead of his time. Euclid's major work, The Elements, is a comprehensive exploration of geometry, number theory, and logic. This magnum opus is structured in a unique way, built upon self-evident truths and postulates, leading us from simplicity to complexity in a series of logical steps. It's like a mathematical symphony, with each theorem and proposition playing its part in the grand composition. Euclid's life might be shrouded in mystery, but his contributions to mathematics are clear and enduring. Euclid brought a unique approach to mathematics, introducing the concept of axiomatic geometry. This revolutionary method involves starting with a set of self-evident truths or axioms, and building upon them to create a comprehensive mathematical system. You see, before Euclid, mathematical proofs were often disjointed and lacked a unifying structure. But Euclid changed this. He began with simple, undeniable truths like, a line can be drawn between any 2 points, and used these as stepping stones to reach more complex conclusions. This was groundbreaking because it provided a systematic, logical method for proving mathematical truths. Instead of relying on intuition or piecemeal evidence, mathematicians could now construct robust, logical arguments grounded in indisputable axioms. It was like constructing a building from the ground up, ensuring each brick was securely in place before adding the next. No longer was mathematics a collection of random facts, but a unified structure, each part supporting the others. This system of building upon self-evident postulates has shaped the way we approach mathematics. Euclid's magnum opus, Elements, is a comprehensive guide to the mathematics of his time, divided into 13 books. Each one is a treasure trove of mathematical wisdom, presenting a unique facet of Euclidean geometry and number theory. The first book sets the stage, introducing the concepts of points, lines, and angles, and culminating in the first major climax, the Pythagorean theorem. Book 2 takes a slight detour, exploring the geometry of areas, while the third book dives into the properties of circles. In Book 4, Euclid examines the construction of regular polygons, a topic that fascinated the ancient Greeks. Then in Book 5 he lays the groundwork for the concept of ratio, a cornerstone of mathematics that underpins the theory of proportions tackled in Book 6. Book 7 marks a shift from geometry to the realm of number theory, with a focus on the properties of whole numbers. The 8th book continues in this vein, exploring the divisions of figures. With Book 9, Euclid returns to number theory, demonstrating the existence of an infinite number of prime numbers. Book 10 delves into the mysterious world of irrational numbers, a concept that was groundbreaking at the time. Books 11 and 12 return to geometry, examining three-dimensional figures, their properties and relationships. Finally, Book 13 caps off Elements with a flourish, presenting constructions of the 5 Platonic solids. Each book in Elements builds on the last, creating a complex, interconnected web of mathematical knowledge. The genius of Euclid's structure lies not just in the breadth of topics covered, but in the logical progression from simple, self-evident truths to intricate and complex theorems. This is the heart of Euclid's enduring legacy, a testament to the power of logical reasoning and the beauty of mathematical truth. Euclid's Elements is renowned for its propositions and theorems, some of which you may recognize. Among the most famous is the Pythagorean theorem. This theorem, found in Book 2 of Elements, states that in a right-angled triangle the square of the hypotenuse is equal to the sum of the squares of the other two sides. It forms the basis for distance calculations not just in geometry, but also in fields as diverse as navigation, physics, and computer graphics. Another standout theorem is the Euclidean algorithm, a practical method for finding the greatest common divisor of two numbers. Nested in Book 7, this algorithm is a prime example of Euclid's knack for merging theory with practicality. Not only does it underpin number theory, but it also plays a key role in modern cryptography. These propositions and theorems have become cornerstones of mathematical understanding. Euclid's fifth postulate, known as the parallel postulate, sparked centuries of debate. Now, this postulate is a bit of a head-scratcher even for the mathematically inclined. It states that if a straight line intersects two other straight lines and the interior angles on one side sum to less than 2 right angles, then the two lines, if extended indefinitely, will at some point meet on that side. Simple, right? Well, not quite. This seemingly straightforward postulate stumped mathematicians for years. They tried to prove it using Euclid's other postulates, but to no avail. This conundrum led to a fascinating discovery. What if the parallel postulate was not universally true? This question gave birth to non-Euclidean geometries, where the parallel postulate does not hold, introducing new and exciting realms of mathematical exploration. This postulate, simple yet profound, has fueled mathematical innovation for over 2,000 years. The influence of Euclid's elements extends far beyond the realm of mathematics. It's not just a collection of geometrical concepts and theorems, but a model for systematic reasoning and logical thinking. Over the centuries, this ancient text has profoundly shaped the way we teach and understand mathematics, molding the minds of countless students around the world. The Elements presents us with a unique approach to problem solving, one that starts with basic, self-evident truths and builds upon them to reveal more complex truths. This method, known as deductive reasoning, is not just confined to the realm of mathematics. It's a fundamental aspect of critical thinking, useful in a wide range of subjects from philosophy to computer science. The influence of Euclid's Elements has also permeated into various fields of practical application. Consider architecture, for example. The principles of Euclidean geometry serve as the bedrock for architectural design, helping architects to create structures that are both aesthetically pleasing and structurally sound. In computer graphics, the concepts of Euclidean geometry are used to create realistic three-dimensional images. Every object that you see in a video game or a computer-animated film is constructed using the principles of Euclidean geometry. Even in the field of engineering, Euclid's Elements plays a crucial role. Engineers rely on the principles of Euclidean geometry to design and construct everything from bridges and buildings to cars and aircraft. Indeed, it's hard to imagine a field that hasn't been touched by Euclid's Elements in some way. It's a testament to the enduring relevance of this ancient text, and to the genius of Euclid, who saw the beauty and power of logical thinking over 2,000 years ago. Euclid's Elements remains a vital part of our intellectual heritage. It teaches us not only the principles of geometry, but also the art of reasoning, the joy of discovery, and the thrill of solving problems. Euclid's Elements, a testament to the power of logical thinking, continues to shape our world today. Euclid's Elements, a work of genius, stands as a pillar in the history of mathematics. It's a testament to the timeless brilliance of Euclid that his work still resonates with us, more than 2,000 years after its initial publication. The Elements is not just a book, it's a universe of logical thought, a testament to the power of reasoning, and a blueprint for mathematical thinking. Its enduring relevance has seen it translated into numerous languages, reaching across cultures and epochs. From Arabic scholars in the Middle Ages to Renaissance thinkers and beyond, the Elements has been a constant companion to those seeking to unlock the secrets of the universe through mathematics. These translations have not merely been linguistic exercises, they've served as a conduit for cultural exchange, with each translation adding a new layer of understanding and perspective to Euclid's work. The commentaries that accompanied these translations have been pivotal too. They've provided a lens through which we can view the evolution of mathematical thought and appreciate the universality of Euclid's principles. Consider the words of the great philosopher Proclus, who wrote in the 5th century, Euclid, who put together the Elements, collecting many of Eudoxus's theorems, perfecting many of Theaetetus's, and also bringing to irrefutable demonstration the things which were only somewhat loosely proved by his predecessors. It's not just the past where Euclid's legacy is felt, it's also in the present and the future. The principles of Euclidean geometry underpin much of modern architecture, computer graphics, and engineering, a testament to their enduring relevance. The Elements continues to be a vital resource for those learning mathematics, its logical structure serving as a model for mathematical reasoning. Euclid's legacy, immortalized in the Elements, continues to inspire mathematicians, educators, and thinkers around the world. His work is a testament to the power of the human mind to unravel the mysteries of the universe, a beacon of knowledge that continues to illuminate our path as we journey through the unending expanse of mathematical discovery.